Calculus-based graphing techniques, part 1. We want to graph the function f of x equals x times e to the x. And the first thing we might want to look at is the domain, and it's pretty clear that the domain of this function is all reals. That is, there's nothing we can't put in here that would make it undefined or have any problems. So the domain is all reals, and the next thing we want to look at is the y-intercept. So we set x to 0, right? And if you put 0 in for x here, you're going to get 0. So we have a y-intercept at 0 and 0. And any time you might want to stop this movie and convince yourself of these ideas, go ahead, and it's a good idea to check these things out, because I'm going to kind of just run right through the problem pretty much until I get to the calculus part. The x-intercept, we set y to 0. When we do that, we can just look at this expression and say, well, the only thing that's going to make this 0 is when x is 0, and of course this is also the y-intercept. Another thing you might notice is that because x can change signs and e to the x cannot, that the function will go through the x-axis when it hits the x-axis. It won't bounce off the x-axis. So the intercept is of the type that the function goes through it, through the x-axis. Intervals on which f of x is increasing and decreasing. We check where the derivative is 0 or undefined. Okay, at places where the derivative is 0 or undefined, we can have local maximums and minimums. That is, the function will change from increasing to decreasing, or decreasing to increasing. And we're very, very interested in local maximum and minimums in order to graph this function in detail. And we're also interested in where the function is increasing and where it's decreasing. So we set the derivative. Here's the derivative of the function. You might stop the movie and convince yourself of this and take the derivative yourself. But there it is. It's a fairly easy derivative that you can get with the product rule. And I'm going to set this derivative to 0, and I quickly notice that e to the x is never 0, so the only thing that can make this 0 is when this expression, this binomial here, is 0. So that would happen at x equals -1. Now, when we want to find this point, we go back to the original function and plug in -1, and we get our critical point, -1 and -1 over e. And that's roughly -1 comma a -1/3, right? E is about 3, close to 3. Just forget an approximation there. So we examine the behavior of the derivative on the number line. I put -1 here, and then I check the sign of the function on this side and the sign of the function on this side. And if I put some negative number over in this region, like -5, I quickly realize that this function is negative. Therefore, it's negative from -infinity all the way to this -1. If I put some positive number in this region here, from -1 to +infinity, say like 10, positive 10, I end up with a positive value. So this is all positive. So that means the derivative is negative on this side, positive on this side. Well, what this means to the function is when the derivative is negative, the function is decreasing. Okay? When the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing. Okay? Now we go over here, and I guess I have to get to the next page here, and I kind of draw crudely function of x on how it's behaving. That means function of x is decreasing, 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 decreasing. It's 0 here, and then increasing, increasing, increasing on into infinity as x heads to a positive infinity. So I know a lot about this. I know that it's the decreasing on this side, increasing on this side, f of x that is, and I also know that the derivative is 0 here, and since it's decreasing and then increasing, this is a local minimum. That makes that a local minimum. So here it is written out exactly what's going on. F is increasing from -1 to positive infinity. It's decreasing from -infinity to -1, and I have a local minimum at -1 comma -1 over e. Now we'll continue this graph in the next video.